and grab them. Back in the box. There's a card for the book, and there's a card for the company, and there's a sticker also if you want to have a zebra cat sticker. So I come from the industry. I'm not an academic. I was working in business technology. Mostly my career has been in health IT. In 2018, I heard about the D-Wave LEAP program and joined that. And I thought it was really fascinating what, this new world of quantum computers and everything that was coming up. So since 2019, I've been basically focused on looking at, from an industry perspective, what can quantum computers do? So in that journey, I have used quite a few of the quantum computers that are out there. At some point, since I've used so many of them, Pact Publishing asked me to write a book about my experience with or challenges with using quantum computers. So there are techniques you have to use to take a real world problem and then embed it so that you can actually use a quantum computer. Now, I'm going to use the word quantum computer loosely because I've worked with what people call quantum-inspired technology, but you can't fully say it's a gate-based quantum computer. So from my perspective, I'm not tied to any one technology. From when you're doing a startup and you're looking at commercial applications and benefits, you're looking for whatever technology can get the job done. So, I know academics are working and certain companies are working on their specific technology, which is great. There's a lot of work needed. But when you have a startup and you're, trying to commercialize and improve a process or some algorithm, then you just have to go with whatever works. Okay, so last year, I was also invited to join QLab. QLab was opened up, I think, November or something timeframe, September or November timeframe last year, and it's a partnership between University of Maryland and IonQ, and they asked me to come join. It's a place where I can collaborate with professors, IonQ staff, and also students. And what I'm bringing to the table is basically my experience with what's happening in the real world, like what are the challenges that we're facing, and like students, like what kind of stuff can you do with a quantum computer, and what is needed, like what does it take to actually use a quantum computer. QLab also has this program where you can apply for credits. Any researcher, I believe, can apply. You don't have to be at University of Maryland. But what it gives you is if you have a project and you can, you apply for it, you can get credits. It allows you to then run your experiments on the IonQ devices. And one researcher on LinkedIn was asking me, why do I need this much money for running on IonQ? And I said it adds up very quickly. So you can one experiment or one test that you do on IonQ can be $100. So by the time you run these tests multiple times, and especially if you have like multiple students or you're going to do multiple trials, the 100 becomes 1,000, 1,000 becomes 10,000 very quickly. So unfortunately, that's where the prices are for quantum computers. So what I'm going to go over is my journey in quantum computing. This is a landscape that I've put together. So basically, I have spanned this whole landscape. And this is not all my experiments. So this is just the ones that I could fit into a 30-minute presentation. So on the on this y-axis over here, what I've got is the simulators at the bottom, I've got gate-based devices, then what we call adiabatic, like the Rydberg atom systems. Then annealing, like D-wave annealers, quantum inspired, which, there are various quantum-based devices, photonic devices that are coming out. They might be using, I don't know, entropy or other things. And then hybrid. And hybrid could be just classical. I mean, how much of that is quantum? I can't tell. So, as long as it's useful. Even the classical simulators or emulators that we are working on now. So you've probably heard NVIDIA has made a big push towards increasing the number of qubits that you can actually work with using the GPUs, A100s, and they've got multiple GPU devices or systems that you can put together where you can go to, hundreds of qubits. So, that's classical, and it takes a long time to run that, but your formulation is still quantum. So you're kind of, the formulation you're going to put over here, which might take a long time, would be the same formulation that you're eventually going to put over here on the gate quantum computers. But it's good practice. It's slow right now, but it's good practice. So I'm going to go over these and just, keep this in mind. The number of qubits or number of variables is on the x-axis. It, again, loosely, it represents the problem size. So, when you're dealing with real world problems, you need 1 million binary variables. So, in a real world application, there is no quantum computer that can do that. But you can get started and you can think about problems that, where would they fit? And so, a lot of people working with gate-based devices are, focused on the hardware, focused on the qubits, the error correction, gate depth, and all of that. But all of that has to be figured out. But when you're in a startup and you're talking to customers, they're like, okay, well, this is my problem, and it's on a server with databases and rules. How would you embed that problem to be solved on a quantum computer? And it's not very easy. Even the most simplified models are not easy to put on a quantum device. So, this is just looking forward a little bit, as some of you will be graduating, and the question will be, are you going to go for research on hardware, or are you going to go into the real world and try to solve real world problems on a quantum computer? And so quantum computers will keep going on their trajectory, and the industry will be putting constant pressure to say, well, what can we do with a quantum computer? So this is kind of like the two worlds meeting together. Okay, so starting at the bottom, very simple problem. You have an equation that you want to minimize. And this is a quadratic equation, x0 square, x1 square, it goes on like that. And then there's quadratic terms like x0, x10. So this is an 11 variable problem, 11 by 11 upper triangular matrix. We're minimizing that. Can we do that on a quantum computer? A few years ago, nobody had done it. So we took this equation, and you have to use, for a gate-based quantum computer, you have to use QAOA, which is quantum approximate optimization algorithm. It's a variational algorithm. You have to tune parameters. It goes back and forth between a classical and a quantum computer. But what I'm showing over here is that if you look at the energy or the cost of that function that I showed, this is the lowest cost, this is the high cost. The whole point of QAOA is to increase the probability of seeing the lowest energy value, right? if a quantum computer can increase the probability of the right answer, which is the minimum cost, then it's going to work, right? That's the whole point of QAOA. And so I'm showing over here that, in fact, I have examples where the minimum cost is the highest probability. And by the time you can get it to like 10% or 20%, if you think about it, then you will find it. I mean, within very few samples. But if you don't do that, then it's just, then you won't be able to find the minimum answer. So I mean, the whole point of quantum computers and quantum algorithms is to increase the probability of the right answer, right? So this was done on a local simulator, right? This was done on IonQ's Harmony. It bumped up some probabilities, but the minimum value barely showed up. And then that was done on IonQ Aria. And the Aria results all came as the simulator results. So as far as Aria is concerned, it's doing a good job. Probably my algorithm isn't doing a good job because it can only do as good as the algorithm. Okay, so then we are moving to the NVIDIA channel, the NVIDIA part that was at the bottom. So we did some experiments. I was working as an advisor to QSecure, and they wanted to know how far can Shor's algorithm go? What can quantum computers do right now with Shor's algorithm? So we did some experiments. Obviously, if you're using Qiskit, I think in Qiskit, there used to be an example of factoring 15. That was about it. So, so we wanted to push that to see, okay, with all the devices that are available, how far can you go with Shor's algorithm? So if you're familiar, Shor's algorithm is the factoring algorithm, which really got the quantum computing industry started. Because there was two aspects for it. One was that you could build a quantum computer that could do factoring. The other one was, well, if you could build a quantum computer that can do factoring, you destroy RSA encryption. So that kind of went in both directions. So we obviously there was no gate quantum computer that could do this, so we needed to use simulator. We use NVIDIA's QQuantum, which, they allow you to put gates, and then those gates algorithm is run on a A100 at that time. Now you can do multiple A100s. So with that, and then the second part is Shor's algorithm right now, Shor's algorithm does modular exponentiation. So it's doing this modular exponentiation over here. So you're increasing the power, and then as you increase the power, you get this remainder. And the remainder repeats itself, so there's a period. And the whole point of the way mathematically you're finding the factors is once you know the period, then later on you can find the factors. So this quantum Fourier transform inverse is able to detect that period. So anything that has a period, this will be able to find it. So you could call this the oracle or the putting in your problem over here. Once you put the problem, then you can solve for it. So a lot of sample algorithms will hard code the period. So the period is 12 or whatever, 4. And then you can find the answer. Okay, you put in 4, you got 4 out. We didn't want to do that. We actually built an algorithm taking Stephen Beauregard's paper, where he actually, when you have to use gates to actually do the modular exponentiation. So this is a generic algorithm where, you just put in basically your function, it does the modular exponentiation on that, and then it looks for the period and finds the factor. So we don't know what the factors are going to be. So with that, we were able to, get the answers. all the x-axis are numbered to factor n. So, this is 100,000, 10,000. And then on the y-axis is different things like simulator time or circuit depth we needed or qubits we needed. So you can see if you're factor a larger number, you need more qubits. And there's two algorithms we could do. For n plus 2, qubits are needed when you can't do mid-circuit measurement. But if you can do mid-circuit measurement, then you can actually reduce the number of qubits. So you can see you're able to get to 5,000 or something. But circuit depth, look at the circuit depth over here. For that problem, we need almost it's 100,000 circuit depths. So there's no quantum computer that can go that far. Within 100 circuit depth, you start getting noise. And then, of course, since this is a simulator, our result came in an hour, an hour and a half. So we got an answer, but it took that long. Ideally, quantum computers would do it faster. Okay, so again, since we don't have that kind of limit, we are looking at other emulators. This is an MPS emulator called Mimic that we tested. Mimic is made by this company called QPerfect. So matrix part state emulators look for efficiencies in the circuit, and they're able to simplify the circuit and go to more qubits. So we can go to 2,000 qubits as long as we have, we can go to 2,000 gate depth as long as we have under maybe 50 qubits. But if we want to do experiments with more than 200, 300, even 1,000, I've seen experiments with 1,000 qubits. We just have to have our circuit depth a little lower. But these type of emulators will actually solve those problems and give 100% accurate answers. So you can see that these alternate methods are being developed so we can continue to do these experiments. All right, so I'm going to go to the analog-based Rydberg atom system. So now we're getting into what I would call single-purpose machines. The gate-based devices are more supposed to be universal, where you can do any kind of logic on them. When you're talking about Rydberg atom systems, if you're only using the adiabatic version, I'm not talking about the digital version. The kind of problems they will solve is maximum independent set problems. So if you have a maximum independent set problem where you have somewhat of a lattice or two-dimensional graph, and you're trying to, determine where should you put some stores, and you don't want a store to be next to another store, then that type of problem is a hard problem to solve classically. And then this device can solve it very quickly. That's what it's made for. Okay, so then let's go to more real world problems. So financial portfolio optimization is, we did this in 2020 timeframe. There were many papers even then, 2019 and earlier, there were many papers on portfolio optimization, but we never saw anyone actually just take this problem and put it on a quantum computer. It's like, can we actually solve this on a quantum computer? So theoretically, yes, there were many papers with that. So it takes a discipline, which is understanding QPOs, quadratic unconstrained binary optimization problems. You have to take a real world problem and you have to formulate it as a QPO. And in the real world problem, there's many constraints. So in the QPO, which is quadratic unconstrained, you have to embed your constraint into the same matrix. So there's some techniques involved there, but you can do it all mathematically. So this is basically the formulation for financial portfolio optimization. That's the risk side. This is the return side. Mathematically, one can create a matrix. I mean, if you can recognize that these are the linear terms that would go on the diagonal of a matrix, if the Q is the binary variable, these are the quadratic terms that would go on the upper part of the matrix. Covariance terms are just the terms that would go in the matrix. And then we have to put and this is the return side, which will convert to a Q as well. It kind of goes into the diagonal. And then you have to put a penalty on that matrix that forces the answers to where you want them to be. So a simple penalty would be, I want a certain number of assets in my answer. Very simple. Then you use the number of assets you want in the answer is the number of qubits that you need in the system. But you can have more complicated penalties or constraints, and then your qubit blows up, basically. That you need a lot of qubits for your variables. Okay, so with that, we just did this experiment. We drew the efficient frontier, we've got the standard deviation and the expected return. The yellow are the classical brute force method. So you just, we had 40 or 60 assets. We had 2 papers. So, I mean, there's a lot of combinations when you're looking at 60 assets and so we're brute forcing that over here on the yellow, which takes some time. The genetic algorithm does pretty good as well, and it's reasonably fast. And then the D-wave annealer, which can do 60 qubits, it can actually go up to about 130, just the 5,000 qubit annealer. So those are the results. The red ones are the results coming from the annealer. So, you put the math in, you run it on the annealer in under 10 seconds, 5 seconds even, or less. You've got the red stuff coming out. So, I mean, we proved that the annealer on this size up to 130 can do this problem. Now, how valuable is this specific problem to the industry? It's on the lower end because, I mean, the real world has many more constraints, many more things that they're trying to figure out. So this is kind of more like a prototype. But it proves the point that a quantum computer can actually, and quantum annealer can actually solve this problem. This problem could be solved on a quantum computer using QAOA. I would need 60 qubits, fully connected. Okay, so we also did a gaming optimization problem where, so this is in the VR environment for anyone of you who has a VR system and gets into that. So this is an environment where you can actually be inside the VR and you can interact with this table has multiple worlds and you can, grab the world and then you go into that world. And one of the things that the client, so I actually worked on this as a consultant, what the client was looking for was optimizing the worlds based on the user's personality or tags or metadata. And so we took those tokens, using the tokens, we kind of did some optimization. We looked at tokens that would match the tokens of the worlds. And then so we displayed the worlds that were the most optimal for that person. It's very similar to portfolio optimization. If you think about it, all these different assets, and you're looking for a portfolio that's the optimal portfolio of assets, this is like the optimal worlds out of all the many thousands of worlds that are out there. Same problem. Over here, we did something a little extra. We took user tokens to run a NPC, non-player character, that sang a song or lyrics. So the song was generated by GPT-3 back in the day before ChatGPT. There was GPT-3. And so what it does is we take the tokens, we optimize the tokens based on, that you can make a matrix of a language or words. So there are some words that are more correlated to other words, like blue is correlated to ocean and sky, and brown may be associated with, other things, trees or bark or whatever, so mountains. So there are a lot of correlations. You can have positive correlations and negative correlations. So that creates a matrix. Those are the quadratic terms on the matrix. And so we took tokens, your interests, to words that might be relevant. And then once we had optimized the words that would be the most appropriate, we fed them into GPT-3 to generate lyrics for a song. And so based on those, it generated lyrics and it sang this thing out. So finally, now we're getting into real world use cases. So this is an infant supply chain optimization problem. It's for procurement managers on how often they should replenish their inventory. So this is a replenishment scheduling problem. We have suppliers and retailers. So you can think of a clothing store, or you can think of a grocery store. You've got items that are being bought, and each item has a different demand, and each location has a different demand. And then what you want is the managers, the procurement manager over there has to replenish those items, right? And you have to keep bringing items in, and you have to decide which supplier you're going to use. And it's an optimization problem because you're looking at the warehousing costs, the purchasing costs, transportation costs, carbon footprint. And then what you're trying to determine is obviously the frequency of how often you should order these items. So should I order this every week, every month? And if I order it, am I going to order a lot and hold it in inventory, or am I just going to be just in time and order it on a very quick schedule? So all of these things have costs associated with it. If I order too much, I have to be worried about my warehousing cost. If I order frequently, then the question is, what are my transportation costs? And what is the, the cost for ordering something all the time? Now, we did this project. So I was at the University of Toronto Creative Destruction Lab. We went through some training, and then we were told to, create a startup. So we created a startup. That's what the ZebraCat is. And now at CDL, every month you're given objectives, and if you don't meet the objectives, then you get kicked out. So, so it was like stress all the time. And you got these, very important people that are part of the committee that are evaluating you, professors at University of Toronto and Waterloo, and they just it's a very brutal program. Plus, you're trying to raise capital. You're trying to see, do you have a real world use case? You have to put your business plan together. You have to get ready. You have to put pitches together for venture capital. So there's a lot going on. So we're looking at a real world use case, and we're saying, okay, well, a quantum computer can do this better and faster than what is happening in the industry. So we started out with a simple formulation. It's a joint, for anyone who's in this area in industrial engineering or any of that stuff, this is a joint replenishment problem. We put that together. We created the QUBO that would be able to put on a quantum computer. That didn't work because we needed so many variables. I mean, there's just no annealer that can solve thousands of variable problems. we got lucky that D-Wave came up with this CQM model, which is a classical, I mean, they call it hybrid, but it's, it's somewhat of a classical solver that D-Wave has created with quadratic and quantum problems in mind. So we started using that. It was not easy to convert this into even their language. It took months to reformulate this into what would work with that solver. And then at the end, like we were at the last month or something, it didn't work. There was like no advantage. There was no advantage to using a quadratic solver for a supply chain optimization problem. And I was like, we're not going to graduate. So, so I was basically working with my partner who's from supply chain. And I said, well, there's no quadratic terms. Why are we even using this thing? Because, the whole point of quantum computers is the strength is in quadratic terms or higher order terms. So I'm like, they just don't exist. I mean, there's a few, but that's not going to give us the advantage. So I said, well, don't you have quadratic terms in your supply chain problems? And he said, sure. We have bundling relationships. Like when you buy two things together, like these two things you buy together versus like you go to the store, you might buy ketchup and mustard together or buy a toothbrush and toothpaste together, but you might not buy certain things together. So I'm like, well, where are the quadratic terms? And he said, most of the world has turned everything into a linear problem because there's no solver that can solve quadratic problems. So the whole world, in the real world, everything has been dumbed down to linear problems. Nobody cares about quadratic terms. And that's why the linear programming solvers do just fine. I mean, they might take a few days to solve the problem, but that's about all they can do. So I said, well, okay, let's put some quadratic terms in here. So we put down bundling discounts and historic order risks. So over time, which suppliers together reduce the risk versus which suppliers together don't reduce the risk, right? I mean, there might be some, like, if the weather goes bad, your one supplier doesn't supply anything to you, but there might be one in another area that doesn't have the weather. The weather is fine, so they will supply stuff to you. So those two are complementary. But you could have two suppliers that are in the same location. So when the weather goes bad in one location, they both are suffering. So that's not a good relationship. That's like a negative correlation. So and then purchasing behavior, what do people buy together? So all of these things are not necessarily costs, but if you're looking at risk, and if you think about financial companies, insurance companies convert risk into a dollar amount, right? What is my cost? And it's kind of probabilistic, but it's still a dollar amount. So we started putting in these quadratic terms of relationships between items. And so those are the extra terms we put in. Those are these extra terms over here. So, which didn't exist before. And so then, of course, we're doing this problem, and it gives these answers of retailer one will order item one on this schedule from this brown supplier, item two on this schedule more frequently from a blue supplier. Like retailer two over here will order the same item from the red supplier on a slightly different schedule. Here is the item one again to retailer three, more frequent and from another supplier. So you see, everyone's ordering things from different suppliers, the different schedules based on discount prices and quantities and costs, right? So this is in the end what we found. These are increasing numbers, trial 0 to 5. you can look at the number of products, 45, 55 to 151. By the time you get to 151, you have these big matrices, 150 by 150 matrix. A lot of quadratic terms in there. There's quadratic terms between the products, there's quadratic terms between the products and the supplies, which that's not really relevant. Just think about a 150 by 150 matrix. So when we did this problem, this brown line is the D-wave hybrid CQM, and that's about less than a minute. This is the classical solver. And the classical solver is the industry's fastest solver. I don't know if I should say the name or not, but anyways, they claim that they're the industry's fastest solver. At 150 by 150 matrix or products, that solver cannot keep up with the D-wave CQM model. It's classical, but it's been optimized for quadratic terms. So this company has been keeping a very close eye on what's happening with the quantum computing industry. They asked me to even give them my formulation so they could see what is it that is slowing down their solver. And they have tried to improve it, but they've got new versions and I've tried it on that. It's not any faster. So even though D-wave CQM is not an annealer, it's not quantum, they're thinking in terms of the new way problems are going to be solved. And that solver gets to within 1% of the best answer. I did some examples afterwards where within 1 minute and 20 seconds, I can get to 1% of the best answer. And the classical solver took more than an hour. And at that point, I just stopped using the classical solver because it was like burning up my laptop. So, okay, so that's it. If anyone wants, they can order the book. And I've got some of these links to starter videos and stuff available if anyone wants to check it out. Any questions? I don't know if there's time for questions, but I'm happy to answer questions.
Can you roll back a slide? Yeah. So do you know what's under the hood of the best classical solver?
The best classical solver is the mixed integer linear programming solver.
Okay.
Standard
linear programming solver to solve effectively quadratic.
Yeah, it's not made for it.
I see. Okay. But so in principle, a specially designed quadratic solver,
which is what D-wave has.
Right. Okay, I get it. So I guess what I'm wondering is like, couldn't you just into a classical algorithm build both, like put both things together?
I mean, there's so many different methods that people are coming up with, I'm sure. I mean, right now D-wave does have a better solver. But I'm sure others will come up with, some other method. This problem has so many constraints in it that you can't use a genetic algorithm either.
Right.
So they just have built a really good solver for this type of problem. And we can go, if you go all the way up to the first, oops, I went out of my slideshow. If you go to the very first slide, when we're dealing with, I mean, this problem that I have is a very complex problem. It's got almost like a recurring, there's like multiple connections between each of the variables, and there's at least 50,000 binary variables that I need.
Okay.
Because of the constraints, you need extra variables. Because of the discrete variables, you use more binary variables. So, I mean, I'm trying to solve over here And there just isn't anything else available, and it just happened that CQM came out at that time when we were in CDL.
Yeah.
So we were able to use it.
That's, go ahead, sorry.
I'm interested in the first page of the program. Can you say more about the requirements of user program that can be approved?
Which,
The
oh,
requirement,
the QLab?
the first page. Yeah, the projects, can I ask the requirement of the projects that can be approved by,
I mean, I think it's just,
submitted?
kind of like, the team and what your goals are. I mean, you can see kind of from here, these are just, I think these are standard research topics that most people are working on. So I think they're not looking for something exceptional. Right? I mean, it's a worthy project that and then you have to also think about, is it something that you can actually run on a, 25 qubit or 30 qubit device? I mean, you wouldn't want to do a supply chain problem over, like over here. So it has to be error correction or, something more related to an INQ device, which is 25 qubits or 30.
I guess just for clarity for the audience, are they seeking more proof of concept projects, or are they seeking more like actual? Do they actually want to see like something with real world impact?
I think that's up. I mean, the committee will probably decide that, but I mean, when I applied they just want people to be able to prove, proof of concepts of whether you're working on something that you need to have tested on a real quantum computer. And if you can add that extra data points, it helps you and helps the industry, then I think that's a worthy cause.
We have a flyer from them and some more information about the requirements of the program. Share with you.
Yeah, I mean, I'm not on the committee that makes the decision, but I don't get the impression that they're looking for this, one special problem. They want people to be able to use the INQ system.
I guess we are about time, so
I have another question. I say the optimization of quantum control engineering. I mean, can they use your physics device directly?
Physics device?
Yeah, because I say the control engineering. I think they might use a low level control to do something.
So I don't know what the exact experiment is over here, but if you're doing something with low level control on an INQ device and you want to test it, I would say apply and put it on, just apply and see what happens.
Okay, thank you.
All right.
thanks to our speaker.
All right.
I think we'll have more